To look at effect of temperature on rate, let's assume we are looking at a reaction of A being consumed to give you products. And when we say to write the rate expression, it's in terms of a constant K times concentration of A to an order of reaction with respect to A. Now K is what we like to see if it's changing based on temperature or not, and apparently it does. If you remember your Maxwell-Boltzmann, at a given temperature, for example 300 degree Kelvin, you would find particles in blue. Only few of these particles have enough energy to react. They have energies bigger than EA. When you increase the temperature by 310 degrees Celsius, remember the curve spreads to the right and the height comes down because we want to have the same area under the curve. But now this time you would have bigger portion of these particles that have energies bigger than EA to react. So it seems that rate at one temperature, for example temperature equal 300 Kelvin, is equal to a constant, let it be K1 times A to power X. And for the same reaction, if you change the temperature by 10 degrees Celsius or 10 degree Kelvin, the rate will have a different constant. And the constant now at higher temperature is bigger than constant at lower temperature. There is a rule of thumb actually for every 10 degrees Celsius that you increase the temperature, the rate doubles because the rate constant gets twice as much. So every 10 degrees Celsius temperature rise means the rate doubles. There is a disclaimer, it only works for reactions that have 55 kilojoules per mole of activation energy. So K2 is approximately twice as much as K1. Now the question is why, and the why was answered in 1880 by Arrhenius, who was able to put them and quantify them and say rate constant is equal to another constant A. Exponentially it changes according to increase in temperature, RT. So this is an Arrhenius constant, so it's a new constant or frequency constant. R is gas constant. We only study usually reactions that are gaseous. T is your temperature. Make sure it is in Kelvin, otherwise it doesn't work. And EA is your activation energy, which is fixed for a reaction. Now this is a little bit annoying, so non-exponential equation for this is natural log of K is equal to minus EA over RT plus natural log of A. Now this looks like equation of straight line. Y equals mx plus b. Meaning if you really want this, Ry is natural log of K. Rx is 1 over temperature in Kelvin, so Kelvin minus 1. Your intercept is natural log of A. Let's look at it a little bit more details. So if you go to data booklet, this equation is given to you as well as non-exponential form of it. And then they can challenge you, and usual question is calculate activation energy and Arrhenius constant A. Exponential is difficult, so if you want to do K versus temperature in Kelvin, you would have a curvature like this and you have difficult time calculating EA. But if you do this, then natural log of K, which is your x-axis, versus 1 over T yields a straight line. Then if you take 2 points on this straight line, you can simply calculate slope. So you have x1, y1, and you have x2, y2, and simply find your slope, which is rise over run, which is y2 minus y1 over x2 minus x1. Now what is your slope? Your slope is simply minus EA over R. Once you have that value, you're looking for EA. EA is nothing but R, your gas constant, which is 8.314 given in your data booklet per mole per Kelvin, times your slope, minus slope. You have to make sure you multiply it by negative slope, because activation energy is always a positive value, minus slope. And that's how we find EA, and that's how you should find. If they challenge you what is natural log of A and then A, you can either plug it in once you have EA, or you can extrapolate this line, and your intercept is natural log of A. Now, a few other things to remember. A is a frequency constant that describes two things: frequency of collisions and also orientation or steric factor of molecules. EA and A are always constant for a given reaction. They are always positive. R is the gas constant. EA has the units of joules per mole. Sometimes you are asked to report it as kilojoule per mole. And A has same units as K, your rate constant, depending on the order of reaction. Now, final things: if temperature is not in Kelvin, everything calculated is wrong. So this is a must.